Hello everyone. Now our today's topic is that the numerical based on practical examples. Okay. In last class we have discussed theoretical importance of sampling distribution and the significance testing and how to do significance testing, the techniques t test, f test, and also we have discussed the confidence intervals. Okay. And today we will try to see with practical examples the how to calculate and how to actually get some conclusion, how do we reach to some conclusion with some practical examples. And here what we have done, here the examples are based on the textile industry. Okay. Data we have taken from textile industry. First is that how to calculate standard deviation, okay, if we know the standard error. So, the standard error, the problem could be like this: for a set of 25 inputs, the standard error is given 12.40. Okay. Then what will be the value of standard deviation? So, we want to know the standard deviation of population, and if we know the value of this standard of error. Okay. So, it is very simple, we know the formula of standard of error. Standard error of mean is the standard deviation of population divided by under root n, where n is the number of input, number of data. So, here if we see the number of data is 25 and standard error is given 12.4. So, 12.4 multiplied by under root n, that is 25, it comes out to be 62. So, 62 is the standard deviation of population, that is and if we want to know variance, variance is this value. So, that way we can calculate, if we know the standard deviation of population, we can calculate the standard error of mean or vice versa. Okay. And also if we know the standard error of mean, suppose standard error of mean is given and standard deviation of population is given, from there we can calculate the n value also. So, using this formula we can calculate. So, one if 2 are given, we can calculate 1, it is very simple one. Now, try to understand, try to go see the next numerical. Next is that the problem is that it is a number of test. It is very important, particularly in industry also, and most important is that it is the in research. In research studies, we must know how many data we have to take to get certain confidence, with a certain data of confidence, with certain confidence limit we can tell, okay, this data, this result is perfect. Okay. So, to determine the number of tests, so in any test the number of individuals to be tested will depend on, so how many tests we have to do. We may test, suppose for any data, any experiment, we may test say 4 sample, we may take 10, we may take 50. So, it cannot be arbitrary. Okay. We should know that how many tests we have to perform. So, it depends upon the variability of the material. Suppose whatever experiment I am doing, whatever product we are developing, we are producing, if it is highly variable, variability is very high, then we have to take large number of data in the sample. We will see in the calculation. Okay. By calculation, by numericals, we will see this experiment, this value, this conclusion we will try to prove. So, the variability of the material, if it is less, suppose the material we are producing which is variability is very less, in that case the number of sample required will be very low. Let us take example of polyester filament, say monofilament, and staple yarn, cotton staple yarn. Now we would like to know the number of data required to calculate the u% or diameter variation. So, as the cotton yarn is highly variable in nature, so to have certain confidence in the data, we have to test large number of data. Okay, we have to test large number of sample. On the other hand, polyester filament, it is coming out, say monofilament, it is coming out from the spinneret, single spinneret, and variability is not there. In that case, obviously we may not need large number of data, and with a certain confidence we can tell that this data result is it is actually valid. So, why? Because the due to the less variability we can, because here standard deviation is less in case of polyester monofilament. So, then next is that the accuracy required from the measurement. Now, if we know, if we say okay, I do not need that much accuracy in my data, okay, its accuracy is not that important, okay, that is okay, it will work, I need only some idea. In that case, number of sample will be less, and if we need highly accurate data, very accurate data, very with the high confidence level, in that case we need large number of data. So, this large number of, smaller number of is okay, but what is that value? So, we will now see how to calculate, how to actually specify the number of test, okay? How to determine the number of test based on known target of accuracy or known variability level. Okay. If we know the variability, or if we have the targeted accuracy error, targeted error value, then we can calculate the number of tests required. For many standard tests, the coefficient of variation is known approximately, so that the number of tests necessary to achieve the given confidence limit and error that can be calculated. So, most of the cases our standard deviation or coefficient of variation is known, and we our targeted error value is given, and then for a certain confidence limit we can calculate the number of tests. So, we must know the variability and we must have the targeted error level, then we can calculate the number of tests with a certain confidence level. So, we can have 95% confidence level, or we can have 99% confidence level. Okay. Now, let us take example. So, calculation of number of tests required. Okay. First problem is that a yarn has mean strength of 10 gram per tex, that is the mean strength, with a standard deviation of 1 gram per tex. This is given. What will be the number of tests which must be carried out, so that at 95% confidence level the maximum error in the estimated mean is 1.9%. That means, what does it mean? The target is that I can allow maximum error percent in my data 1.96%, that is the allowable data. So, beyond that I cannot allow 2% data, whatever reading I am taking. So, I can allow only 1.96% maximum error, and maximum error of 1.96% of what? 1.96% of 10 gram per tex, 10 data, that is the mean value. So, the mean can vary 1.96% plus side or 1.96% minus side. Within that range it is allowed, and standard deviation is known, and I have to calculate at 95% confidence limit. Okay. Now, what are the given data? Mean strength is given 10 gram per tex. Okay. Next, what is given? Mean deviation is given, standard deviation is given, it is 1 gram per tex is standard deviation. Now, maximum error it is given in percent, it is not in value. So, that in that case we have to convert it to in terms of value. So, 1.96% of 10, what is that? It is a 0.196, that is the 0.196. 0.196 is the maximum limit that is allowable. What is that limit? 0.196, that limit is that it is the standard, it is a t value multiplied by standard error. This t value that we have seen earlier, that limit, the maximum limit is d value, d, the d we have seen it is a t multiplied by standard error, that is the maximum limit of that a. It can be, it can go into plus side and minus side. Okay. And this, why this t value is 1.96? Because we have large number of data which we can consider as infinite, and from the t table at 95% confidence level, if we see the t table, and this t table will give us the value, this is the 95% confidence level, and here if I little bit enlarge at infinite level, the large sample, infinite level means which is large sample, it represents, it is a 1.96. This 1.96 is the t value, and here this t value is taken here. So, that limit means the maximum limit allowable is equal to 1.96 from the t value we have, t table we have got, and multiplied by standard error. And what is the limit of mean? That limit of mean that we have calculated already, this limit of mean is the, it is a maximum error allowable, and maximum error allowable what we have seen earlier, it is a 0.196, that is 1.96% of 10. So, 0.196 is the maximum error multiplied by standard deviation, equal to standard deviation multiplied by 1.96. Okay. And so, we get the, we can calculate the standard error of mean. From here we calculate the standard error of mean. What is this value? Standard error, it is a 1 by 10, so 0.1. So, standard error we have calculated. Now, our target is to calculate the number of sample tested. So, what we have done? We have calculated the standard error, okay, knowing the limit error, okay, maximum error from there, and 1.96 the data came from the confidence level. Okay. So, the formula says that standard error of mean equal to standard deviation of population by under root n. N is the number of sample and n is the number of sample, and standard deviation is given already. It is a population standard deviation is given 1 gram per text. So, from there we can calculate the value of n. So, 1 by 10 which is standard error, this is the standard error. So, standard error 1 by 10, okay, equal to 1. What is 1? This 1 is the standard deviation, okay, and divided by under root n. This is the number of sample which we want to calculate. Okay. So, under root n equal to 10 and n will be equal to 100. Okay. So, this is the answer. So, if we take now the conclusion is, if we take 100 test, 100 reading, 100 sample, okay, and in that case we can tell with 95% confidence that the test result, whatever test result is there, sample result, the error will be, maximum error will be 1.96%. So, the significance of this test is that we can tell at certain confidence. Now, suppose we want to shift our confidence, we want to shift our confidence to 99%. Now, what will happen to the number of tests? In that case, if we shift the confidence, if we want to have more confidence, in that case our number of tests has to be more. Now, let us see with the same example, just by changing the confidence level, let us try to see the calculate the number of samples. Now, here the problem is exactly same. Yarn has mean strength 10 gram per text with a standard deviation of 1 gram per text. What will be the number of tests which must be conducted, so that 99% at 99% confidence level, maximum error in the estimated mean is 1.96%. Earlier also it was there, but the error was 1.96%, but if we take 100 reading, that means out of 100 time, 5 times I will be wrong, 5 times there will be the data may cross these things. But if we try to know at 99% confidence level, that means we want to miss only 1%, but 99% time I will be correct. So, let us see what will be the number of tests required. The same way it will go, mean strength, standard deviation, maximum error in the estimated mean strength, that is 1.96%, that is maximum error, and maximum error value is exactly same, and here only thing is that it's changed to 99%. So, with 99%, what is changing here? Here the t value has got changed. Earlier it was 1.96, at 99% confidence level with say large number of data. Let us see with large number of data, it has become at 99% confidence level, it has become 2.576. It is approximately, we can consider it is a 2.58. So, as it has become 2.58, that means everything will get changed. So, then in that case, so this limit is same, but the as it has become 2.58. So, standard error will get changed. So, this is the maximum error is 0.196, it has become. So, standard error earlier was 0.1, now it has become 0.076, because of the fact it has earlier it was 1.96, now it has become 2.58. So, standard error is changed, and in the same way we can calculate the number of sample. So, standard error 0.076 equal to 1 has come from, this is the 1 standard deviation, okay, and this is the standard error, okay, and from there we can calculate the number under root n equal to 13.16 and n has become 173. So, what does it mean here? Earlier if we test based on 100 data, 100 reading, then my confidence is 95%. That means, out of 100 data 5 will definitely go above that. But if we want more higher confidence, if we need higher confidence, in that case we have to go for the large number of data, that is 173. So, if we want to have more and more confidence, higher confidence, so in that case some number of sample will be more. Now, this is one way of looking at. Suppose we will go back to the earlier problem once again, 95% confidence level. Okay. In that case, now I am not going to allow 1.96% error, that is too much for me. For our experiment, this experiment needs very close limit, okay, that is a wide limit. In that, now next example is that the same 95% is there, but here what we have done, I am not allowing 1.96% of the error, okay, that is not, it is not allowed, it is allowed only 1.25%. That is my that is the error my experiment will allow, that because the amount of threat or amount of accuracy required or depending on the type of test. Okay. In that case, suppose we want to test some material which the actual result may give us the live threat, like bulletproof vest, the penetration efficiency we want. In that case, the errors must be very small. Okay. So, in that case, so if we reduce the number of error, then to have certain confidence, what will be the number of data test required. Okay. So, from 1.96 we have reduced it to 1.25. Okay. Now, let us see the impact. So, mean strength is exactly same. Now, standard deviation is same, maximum error has got changed 1.25. So, now we will calculate the maximum error, it has become 0.125, earlier it was 0.196. Now, confidence level is same, that is why it has become it remains at 1.96, okay, and standard of error, from there we can calculate the standard error. So, standard error will be 0.125 by 1.96. So, standard error has become 0.064. This is the standard error. Okay. And if we know the standard error and our standard deviation is known, so we can calculate the number of sample. So, this is the standard error and standard deviation is given, and we can calculate the number of sample and number of samples become very high, 246. So, that as our requirement is becoming stringent, so we have to select, we have to take large number of sample. Okay. So, we have seen here the number of sample depends on two parameters. One is that variability of sample, or another is level of confidence we require, and the range error allowable. What is the error allowed? That we have discussed. Now, come to the next type of numerical. This is the value. Now, here calculation of number of tests required with lower allowed error. Okay. So, at different number of allowed error. Here the thing is that we do not know the standard deviation. In earlier problem, the standard deviation was given. Here the one little bit complexity is there. Here standard deviation is not given. So, we have to first calculate the standard deviation. Now, the numerical is that 99% confidence range of the mean yarn strength based on 64 test sample is plus minus 8. Only we know the confidence range. Okay. We do not know the even mean value. What will be the number of test samples required to obtain 99% confidence range of plus minus 4 of the yarn strength. So, confidence limit is same. So, 99% confidence limit is same, only thing is the range has changed. So, initially 64 tests were conducted and confidence range was plus minus 8. Now, we have reduced the confidence range. Okay. That is the, it has become plus minus 4. What we have done here, the error has been reduced, we try to reduce the error limit. So, standard deviation is not known here. So, for 99% confidence range, the limit of mean, what is that? Because as it is 99%, as we have seen earlier, it will be t value is 2.58 multiplied by standard error. So, what is that limit here? Plus minus 8 equal to 2.58 multiplied by standard error. Okay. And standard error will be plus minus 8 divided by plus minus 2.58, this is the value. So, standard error is 8 by 2.58. Okay. This is the standard error of mean. So, standard error equal to standard deviation of population by under root n. So, n is the number of sample. What is here? What is n value here? It is a 64. So, n value is given 64. So, standard error is known, n is given. So, from there, so 8 by 2.58 is the standard error, 64 is given. From there we can calculate the sigma, that is standard deviation of the sample. It is a standard deviation of population, it is a 24.8. So, now this standard deviation we will use in the next segment, second part. For limit of plus minus 4, so this is plus minus 4, again it has large sample 2.58. So, from there standard error we have calculated. So, this is the 1.5 is the standard error. So, now we know the standard error and we know the mean population standard deviation. Standard error is known for this plus minus 4 error, and standard deviation of population is known. So, from there we can calculate the n value. So, this is the number of sample should be test taken to have the limit of plus minus 4 for same population. That means, from plus minus 8 error, where we required only 64 test samples, when we are changing it to plus minus 4, the sample required, number of sample required 256. That means, if we take 256 sample, so with that 99% confidence level, level, we can tell that the error will be maximum plus minus 8. Okay. Now, next problem is that we have this is now the significance test. Till now what we have done, we tried to calculate the number of tests required. Now, this is the significance test, which is single mean with a small sample. So, small sample typically we assume at less than 30 number of sample is there. If it is there, it is a small sample. Now, the problem is that the 24 ring bobbins are tested. We have tested 24 ring bobbins for count, and the mean count is found to be 52.4. Okay. And the standard deviation of the sample we have got 4.1, that is the standard deviation, and the nominal count of the yarn, which is supposed to be 50. So, that is targeted count is 50, but the when sample is taken 24 ring bobbins are taken and we have got the count of 52.4 and with the standard deviation of 4.1, that is a sample standard deviation. Here population standard deviation is not known. So, in that case, specific case, we can assume the population sample standard deviation as population standard deviation, because we do not have any data. Now, we have to tell that whether the yarn is too fine, that means, this is 50's count and it is a 52.4 count. The question is that is the yarn is fine, it is too fine. Should we take precaution? Should we take any action? Should we make it little bit coarser by changing the draft? So, all this question, so suddenly changing draft, it is not that easy. Suppose we have tested 24 ring bobbin, we have got 52.4. Suddenly based on that, okay, this is coming finer, 50 count is targeted, 52.4 count is coming. So, before we take any action, we cannot stop the machine, we cannot halt everything. So, that takes time, that is expensive one. Before that, we have to quickly do the significance test. Significance test means, if we assume, if we see that, or if we can conclude that this difference is not significant, then we will let the process go, and this it will not have any significant impact on any other properties. But if this difference is actually significant, then we have to stop, we have to take precaution. Okay. That is the basic reason of the significance test. Okay. So, now we have to decide whether the yarn is actually finer or not. Okay. Now, the solution is that what are the given data? The number of sample is 24, okay, and mean of sample is 52.4, that is the mean. Standard deviation is 4.1, that is the standard deviation, and nominal count is 50, that is the targeted count 50, that has to be produced. But when we have tested sample has come 52.4. Now, how to do it? Here we have to do T test. So, we have to calculate the T, and we know the T how to calculate the T. To calculate the T, we have to first calculate the standard error of the mean. So, standard error of mean of bobbin, we have to how to calculate the same formula, standard deviation by under root n. Okay. So, here standard deviation is known and number of bobbin is 24 sample. So, standard error is calculated 0.837. Okay. Now, if we calculate, now once we calculate standard error, then we can calculate the T value. What is T value? From earlier curves we have diagram we have seen that T is its modulus of nominal mean minus sample mean by standard error. Okay. So, let us calculate the T value. This is the T value 2.867. Okay. So, this is 50 minus 52.4 by standard error, 2.4 by the standard error we have calculated in last slide we have calculated 0.836 was the 7. So, by 0.837. So, 2.867 is the T value. Now, this T value we have to compare with the table T value for a particular degree of freedom, that is Z value, degree of freedom, which is nothing but n minus 1 number of sample. So, we have 24 samples. So, degree of freedom has become 23. So, for that particular T value, particular degree of freedom, from the table we can calculate, we can get the T value. So, and then compare this T value obtained here 2 in the step 2 with the 5% and 1% value of T for degree of freedom of 23. Okay. So, at 5% level the value of T is 2.069 and at 1% level value of T is 2.807. This is for the degree of freedom of 23. Let us see from the table at 5% level, we will see that degree of freedom is 23. At 5% level, this is the 95%, 90. So, 95% level it is a 2.069, okay, and it is a 2.808. So, this with these two values we can compare the results, okay. 2.069 and 2.807, these are taken from the table, okay, and our calculated value is what we have achieved, this 2.867. Now, this 2.867 when we compare with this table value, it is higher than both this value, higher than 1% level. That means, what our conclusion is that 2.867 is more than 2 at 1% level, 1% level is always higher than the 5% level, it is greater than 2.807. So, we conclude that the ring bobbin is spinning. So, ring frame is spinning too fine count, okay, because the difference between the sample mean and nominal mean is significant at 1% level. So, that real difference exists. So, if it is there, then what action we have to take? We have to stop the machine, we have to stop the production, we have to do the correction, we have to all the corrective action we have to take. Okay. Now, with the same data, same problem, we have changed here. What we have changed? That the 24 ring bobbins are there, same ring bobbins now are tested for count, and the mean is found to be 51.8. earlier it was higher. Now, we have tested, the count has become closer to the nominal value. Earlier if we see, earlier what it was 52.4, okay. Now it has become 51.8. Okay. Now, we have to test, okay, whether the yarn is still fine or not. Okay. Same way we will go, number of sample is the sample mean is 51.8, standard deviation is 4.1, it is given, nominal count is same step 1, and standard error is same, because the number of sample and the standard deviation was same. Only difference is that here the sample mean, and sample mean has become 51.8. So, the t value has become 2.15 and degree of freedom is 23, and for 2.15 23. So, it was the at 5% level it was 2.069, and at 1% level it is 2.807. So, our calculated value is 2.15. So, what does it mean? That means this value is lying in between 5% level and 1% level. That means, although there is variation, okay, but we cannot confidently tell that it is a real variation. Okay. So, this 2.807 is more than 2.1.15 is. So, this is in between. The conclusion is that although there is some evidence of a difference in variability, but is only significant at 5% level, it is only significant at 5%. So, that depends on us how to tackle these things. Okay. Now, next is that significant test between means of two large sample. Now, earlier till now what we have done? We have done significance test based on the nominal value. So, nominal value is known, our target, suppose our ring frame is targeting, as I have said, it is a 50s count is targeted. So, we have taken sample out of that and we have done test on this, but this type of experiment is very much required in research, where we have two samples, two separate both the samples are there. In that case, suppose we have selected one sample of yarn A, another sample we have taken sample of yarn B. Now, we would like to compare these two samples. When we try to compare the two individual sample for their significance, then we have to use some different methods. Now, let us see this example. From this example it will be very clear. Now, two yarns each of 45 NE count, okay, 45 NE count is known, where these were tested for least strength. 20 tests were made on each yarn and the following results were obtained. So, yarn A 20 test, yarn B 20 test, mean strength here is 60 pound, okay, and here it is 70 mean strength, and standard deviation here is sigma 1 is 6.5 and here sigma 2 is 7.8. Now, what we were interested in, whether this 60 and 70, whether the yarn B is significantly stronger than yarn A or yarn A is significantly weaker than yarn B, that we have to test. So, do we right away reject the yarn A? So, that we have to test. Okay. Suppose we have two samples from two suppliers, yarn A and yarn B, we have to select one of them. Okay. Now, and suppose this yarn A is giving in little bit cheaper price yarn A. Now, then suppose this the prices are same, then we will definitely go by this yarn B, but yarn A when they are offering us some discount, say then we have to take decision. But at the same time it is said that we cannot compromise our strength. Okay. Now, what we have to do? We have to the option with us that before taking finalization, before rejection, we can take one chance, because we cannot compromise with the strength. So, we can reject, but before rejection we will do some test, significance test. Now, if the significance test says this difference is significant, then we will reject it. If it is insignificant, then we may decide to take this one. Okay. Now, what we do? Standard error of mean of yarn A. So, like earlier processes, we will calculate the standard error of yarn A. So, AC 1 same way 66.5 by under root 2, this is the standard error of 1 A. Similarly, for yarn B, standard error 2 is equal to 1.75. Now, what are we doing here? We are trying to calculate the significance of the difference of mean. So, in that case we have to calculate the standard error of difference of mean. So, it is not the standard error of mean, because our target is that to test the significant difference of mean. So, the from standard error of 1 and standard error of 2, we can calculate the standard error of the difference between mean, which is known as AC difference. Okay. And using a simple formula, this is the standard formula given. So, from AC 1 and AC 2, what we do? We calculate AC difference. Okay. So, what is the formula? AC difference is under root AC 1 square plus AC 2 square. Okay. And AC 1 and AC 2 is known. So, from there we calculate the standard error of difference. Okay. Now, this standard error will be treated as normal standard error as we have done earlier. Okay. But here as we have two standard error and we want to calculate the, we want to understand the difference, we have to take the decision on the difference in mean, that is why we have to calculate the standard error of difference. Okay. AC difference has become 2.265, and this 2.265 is the standard error of difference, and then we will treat exactly in the same way. Here only thing difference is that here earlier case we have used the standard error, but here we are using standard error of difference with the same way, because here we have two individual means. Okay. Now, T is 60 minus 70 by standard error of difference, and we know the standard error of difference is 2.265. So, T value has become 4.415. So, this is the T value, and our degree of freedom was, that is the large sample. So, for large sample it is the for 95 and 99% it is 1.96 and 2.58 as we have seen earlier also, and this is for both the it is a very high. Okay. T value is very, that means what will be our conclusion? Our conclusion would be there is a real difference is there, since 4.415 is greater than 2.58, the difference between the mean Lee strength is significant at 1% level, that is real difference exists. So, in that case, in this case what our decision would be, we must reject that one yarn A, which is of 60 strength. Okay. Yarn strength we can yarn A we can reject and we can retain the yarn B. Okay. So, this is what about the significance difference in mean. Okay. And next segment, okay, real difference is there. In next segment we will discuss the significant testing of dispersion. Okay. So, significant testing of dispersion is of basically it's the problem is here the mean difference is there, mean difference there is no difference. Okay. Suppose the mean earlier till now what we have seen, the yarn there is which is weaker or which is stronger, which is more variable, or so that is the mean value, and difference we are trying to understand, and if there is any significant difference in mean value, then we are taking proper action. So, like last problem, last numerical what we have seen, where the weaker yarn which is that is 60 pound the strength, we have rejected straight away. Okay. Now, the here in the significant test in dispersion, what we will discuss here, suppose two sample, in one sample the variability is high, another is variability is low. So, in that case should we, which sample should we take with higher value variability, that means it is always it is not desirable to have higher variability, but if the machine is producing higher variability, should we take immediate action or not. So, that all these things we will discuss in the next class. Okay. Till then, thank you.